Okay, so today we will talk about the communicating enthalpy. Why is it important to communicate enthalpy, and why do we designate one topic into how to communicate enthalpy? It is important because it doesn't really matter how much do you know in your brain, but you should be able to communicate what do you know. And so to help you and everyone in the world have the same language per se, quote unquote, of how are we communicating enthalpy, we have established 4 ways on communicating enthalpy. In your textbook on page 495 and on, you will see them as methods. I prefer to say them ways, but it's the same thing. So the first one, method one on communicating enthalpy is using that is known as the molar enthalpy of reaction. Now, when we are saying the first method, doesn't mean that if I say method one, then I mean molar enthalpy. But it is one of the ways, the one way to communicate enthalpy is using molar enthalpy. We talked about what is molar enthalpy. So if we have a reaction, then we are writing it in terms of the compound that we are interested in as 1 mole. And on this case, what you will see is the enthalpy written in the reaction as the molar enthalpy. The difference between the just enthalpy change and the molar enthalpy change is that the enthalpy is just a reaction H, so where reaction can be combustion and then we say C, or it can be formation where we say F. And when we are talking about the molar enthalpy, then we have the letter M right beside the H, indicating that this is molar. And the reaction again can be combustion or can be formation. And if it is combustion, then we say C. If it is formation, then we say F. But both of them in a common name are with the letter R. So when let's suppose that we have the formation of an element. We'll go to the data booklet on page 4 and 5, and then you see at the top of the data booklet, you have a standard molar enthalpy of formation at 298.15 Kelvin. So what does that mean is that when we are talking about the standard conditions, then in order to identify that we are dealing with standard conditions, what do? Is we add a 0 on top of the H to indicate that we are having standard condition. Standard conditions. Good. So now, when we take a look at those pages 4 and 5 in your data booklet, what you will notice is some compounds in which the formation, molar enthalpy of formation is given. When we are stating molar enthalpy of formation, it is formed from its basic elements. If there are 2 elements, then what do we have? Let's say manganese 4 oxide, you have manganese M oxide giving you manganese 4 oxide. So even if you have 4 elements, like in the case of ammonium chloride, NH4Cl, as the reaction, you are writing N2 plus H2 plus Cl2 gives you NH4Cl. So N2 plus H2 plus CO2 gives you NH4Cl. So always you have to go to the elements that is the compound is formed at, not uh, let's say HCl and N2, but to the basic element that this is formed to. Like in the case of barium carbonate, when we have barium plus carbon plus O2 gives you barium carbonate. Okay, so this is what it means when we are looking at those numbers in the pages 4 and 5 of your data booklet. Is it clear? Okay. So the name of the compounds is sorted alphabetically, starting with aluminum oxide and ending up with zinc sulfate. And then the second column is the chemical formula. And this is probably the best friend for you if you are wondering what is the formula, along with pages 9 and 10, that acids and bases are there. But those 4 pages will be your best friend when you are wondering what is the chemical formula that this compound has. And then the last column is telling you what is the enthalpy of formation at standard, molar enthalpy of formation at standard conditions. And it is kilojoules per mole. 100% of the cases that you will see in terms of the formation are that we are dealing with standard conditions, even if they are not mentioned. But in general, they are mentioned. So as you see here, what those numbers mean when we are talking about, let's say, aluminum oxide. So aluminum and oxygen are reacting together to form aluminum oxide. And the molar enthalpy of formation in standard conditions is negative 165, sorry, 75.7 kilojoules per mole. Let's balance this reaction. As the balance, this will be 4, 3, and 2. And then you see that you have 4 moles, this is what it means when we have those coefficients. 4 moles of aluminum are reacting with 3 moles of oxygen gas to produce 2 moles of aluminum oxide. Okay, but what we have here from the data booklet is actually 1 mole. So therefore, what do is we write this, if we want to express the molar formation, then we write the moles in front of aluminum oxide as 1. So in other words, we divide by 2 all of the coefficients in the reaction, in the balanced reaction. So 4 divided by 2 will be 2 aluminum plus 3 divided by 2 is 1.5 oxygen, and then we have 1 aluminum oxide. And on this case, the formation, the molar formation in standard condition will be negative 1,675.7 kilojoules per mole. So when the balanced reaction has in front of the compound of our interest doesn't have the coefficient of 1, and we are using this method, the molar formation or molar enthalpy, then what do is we make that as a coefficient of 1. In other words, we express the coefficient in some cases as fraction. So if you see and if you are asked to communicate enthalpy as the molar enthalpy, that being the formation, combustion, or reaction in general, for a specific compound, you will go to that compound and then see in the balanced reaction, is that coefficient in front of the compound 1 or yes or no. If it is, then that is the number that you have to put it in. If it is not, then make it 1 and then rewrite it with that number. Now, the second method that we use to communicate the enthalpy, or the second way that we communicate the enthalpy, is when we are using the enthalpy of the reaction. So when we have, let's suppose, I will take ammonia. So formation of ammonia. So as a second method, method 2 is the enthalpy of reaction. I will take ammonia so that we see the enthalpy of the reaction. So then we have N2 plus H2. I'm not worried about the state of matter here because that is not my focus now. NH3. Okay, and then what do we have from the data booklet? The enthalpy of formation, molar enthalpy of formation at standard conditions is negative 45.9 kilojoules per mole. Good. Let's see now, how can we balance this reaction? This will be the balanced reaction. Okay, so as you see here in the balanced reaction, what do we have is 1 mole of nitrogen is reacting with 3 moles of hydrogen to form 2 moles of ammonia. But the information that we have from the data booklet is that if 1 mole of ammonia is formed, then 45.9 kilojoules is released to the environment. What about when 2 moles are formed? Now, what is the enthalpy of the reaction? What is it? So if 1 mole is, when it is formed, of ammonia is formed, is releasing to the environment 45.9 kilojoules, then when 2 moles are formed, then the enthalpy of formation, but now is not the molar enthalpy, so don't write the M, is 2. Why 2? Because 2 moles are in the balanced reaction times negative 45.9 kilojoules per mole, and this will be 91.8, negative 91.8 kilojoules. Let's stick with this reaction. So let's bring this reaction again. So now we have N2 plus 3H2. This is the reaction, the balanced reaction, NH3. And then from the data booklet, the molar formation is a negative 45.9 kilojoules per mole. What if I tell you that as a result of the reaction, then we have here, we have 5.5 moles of ammonia formed for some reasons. So we have 5.5 moles of ammonia formed. What will be the enthalpy of formation for this reaction? What should we do to this number here, that is the formation of ammonia from its basic elements? What should we do to figure out what is the for the enthalpy of the reaction when 5.5 moles of ammonia are produced. What should we do? Multiplied by 5.5. So then we'll have 5.5 times negative 45.9. And this is even in Stoic, it works because we have moles here. So we have 5.5 moles times negative 45.9 kilojoules per mole. So moles and moles is canceled out. So the enthalpy of formation of 5.5, yes, do Stoic, 5.5 moles is negative 252.5 kilojoules, just to, or to keep the correct sig digs will be negative 253 kilojoules. So this will be your final answer. So when we are writing, when we are expressing, when we are communicating the enthalpy of the reaction and using the standard molar enthalpy of formation, then we have to multiply whatever number of moles is produced in the reaction by the standard molar enthalpy of formation. Now, we are talking here about, oh, sometimes it's negative, sometimes it's positive. Even in your data booklet, you will notice that sometimes it's positive, which is not even stated because it meant positive, and sometimes it's negative. Now, let's talk a bit about this positive and negative sign that is used at the enthalpy. Okay, before we move to the third method, that is the enthalpy as part of the reaction. So when it is an exothermic reaction, so exothermic reaction means that what do you have, what is happening in the reaction? It is giving the energy to, or heat to the environment. Remember what we said. We have two parts. We have the system, or also known as the reaction, and we have the surrounding. In calorimetry or anywhere, we observe the surrounding because we cannot see specifically. It's very hard to figure out what is happening in the reaction. We observe the surrounding, we have an eye on the surrounding, and based on this, we draw the conclusion as what is happening in the reaction. If the surrounding is heated up, so temperature of water in the case of calorimetry is raised up, then what it means, based on the conservation law of energy, this energy is absorbed from the system, the reaction, meaning that the potential energy of the reaction is dropped because some part of it is taken to go to the surrounding. Okay, so in exothermic reaction, what do we see is that surrounding is heated up, is the temperature is going up. Also, what we notice is that the potential energy of system known as the reaction is going down. If something is, if you have, let's say, 5 apples and someone is taking 2, then you are left with 3. Okay, so the potential energy is going, it's going down of the reaction, okay, of the system, I mean. Now, what it is going on this case is that this energy that is absorbed, is released from the system, from the reaction, is going to the product side, okay? So the energy released from system is going to the product, toward products. Because remember what we said, that we have two parts. This is basic chemistry. Two parts on the reaction: reactant and products. So the energy now is going to the product side of the reaction. And the way that we communicate this in terms of the sign is using this negative sign here. So it is then when we are expressing it either as a formation or molar formation or reaction, anything, enthalpy change, then the enthalpy is negative. So this is how we indicate that we are dealing with an exothermic reaction. For the endothermic reaction, the opposite thing is happening. So when we have an endothermic reaction, then the surrounded is cooled down. Potential energy of, so it's cooled down, meaning that some heat, some energy is absorbed from the system, from the reaction, by the system, from the surrounding. Okay, so potential, if you are taking now, if the system is taking, then potential energy of the system is increased. Okay, and then the energy, if it is increased, this energy is absorbed now, is absorbed by the system. The energy is absorbed by the system. And every time that we say the system means the reaction, and it is going toward reaction. Why is it going toward reaction? Reactants. In order for the reaction to happen, you need more heat. Therefore, the reactant needs more heat to make the product happen, to make the other side of the reaction happening. And the sign that we use for the enthalpy is positive. When it is positive, as we do in math and in chemistry, we do not always state it, but if it is not stated, it means that is positive. The third method that we use to express the enthalpy is when the enthalpy, to communicate the enthalpy, is when the enthalpy is in terms of the balanced reaction. So as part, I will say here, is as a part of balanced reaction. You have to see if it is positive, if it is negative, if it is going toward the reactant, if it is going to the product, if you have gathered that information, let's say formation, of the compound from the data booklet, then you have to consider in a balanced reaction, is it 1 mole or is it more than 1 mole, and so on and so forth. So let's suppose that we have the formation of of ethane. Okay, so formation of ethane. Ethane, when you see it in your data booklet, is a formation of ethane is uh, is sorry, hydrogen and carbon, and they are forming together C2H6. Okay, and from the data booklet, the molar formation at standard condition is negative 84.0 kilojoules per mole. Let's balance this. So the balance reaction will be 3, 2, and 1. Okay, good. Now, the fact that we have a negative sign, what does this mean? Is it an exo or is it an endothermic reaction? It's an exothermic reaction. Will this reaction be on the product or on the reactant side of the reaction? With this number be on the product? Okay, good. On the product side of the reaction. Great. Now this is the molar. Is the last question is the balanced reaction with 1 mole or more than 1? Is it with 1 mole? Therefore, when we express the enthalpy as part of the reaction, then we will write it as 3 hydrogen plus 2 carbon will give you 1 mole of ethane, and then plus 84.0 kilojoules. Make sense? Does it make sense, guys? If in the balanced reaction we didn't have 1 mole, then we'll multiply this number that we have from the data booklet and write it into the appropriate part, that being product or reactant, with the multiplied by the coefficient that is in front of the compound in the balanced reaction. The fourth and last method that we communicate enthalpy is through graphing, method 4. And I will say just diagram, potential energy diagram. Keep in mind, guys, that we always are looking from the perspective of the system. Can we put the number, in that case 45, whatever was it, in the reactant side with negative sign? No, you can't. Where is it? First of all, you cannot have a negative energy in the reaction. And then where is it placed is telling us what type of reaction is it. So if it is placed on the product, means that it's released to the environment, means that it's an exothermic reaction. And when it is placed in the reactant, means that it's absorbed from the surrounding to the system. So it is telling us where is it going, the place of the enthalpy, if it is on the product or if it is on the reactant. The value, and it's always with plus. I haven't seen any reaction, balanced reaction, where one of the compounds has the negative sign. It's always plus. And the number is as a result of the uh, multiplying by the coefficient that is in front of the balanced reaction. So if we have now an exothermic reaction, what it means is that the energy, kinetic and potential, which we know it with the name as enthalpy, of the system is dropped down. So in the vertical axis, what do we have is that it is known as the potential energy of the system, which can be in kilojoules or in joules. And on the vertical, or sorry, on the horizontal, we have the reaction. So the reaction that is happening. Now, when we are dealing with an exothermic reaction, means what? The energy of the system, of everything that is participating in the reaction, is dropped. So the graph will look something like this. Here are the reactants, and then it is dropped to a certain point, and here we have products. This change is whatever is the change of enthalpy for the reaction. If it is molar, then you will write the reactants and product as in 1 mole. If it is a balanced reaction, then you will take into consideration the coefficient in front of them, and then express the enthalpy change based on that coefficient. So in the difference, when we have an endothermic reaction, because this one is exothermic reaction, when we have an endothermic reaction, what do we see is that the reactant has less energy, potential energy, than the products, because it is absorbing this energy from the surrounding. And here we have the reaction. And this type of reaction, this graph that you see here, where the potential energy is less than the potential of the reactant is less than the potential energy of the product, is known as the endothermic reaction. So those are the four ways that we represent or we communicate the enthalpy change of the reaction, that being the molar, or being the reaction itself, or so on and so forth. And then, so the summary of communicating enthalpy is this one here. It's kind of a table. So we have 2 types of reaction. We have exothermic reaction, and we have endothermic reaction. And on the other hand, what do we have? We have 4 ways of communicating it. The first one is molar and using molar enthalpy. The way that we express it is delta R, where R can be combustion, formation, or just the general R, and then H for the enthalpy and M for molar. And in an exothermic reaction, this is negative, while in the endothermic reaction, this is positive. Okay, The second way of communicating enthalpy is just with the enthalpy change of the whole reaction. So enthalpy change of reaction. Keep in mind here, at this method, you must have the compound of your interest in 1 mole in the balanced reaction. Okay, and here you just have a balanced reaction. Balanced reaction. Again, here, what do you see? You write the reaction as reactants and then products. It's a balanced reaction, and then you express the enthalpy as negative on the side of the reaction. And here you have a balanced reaction, so reactants and then products, and then you express the enthalpy as the positive one. As I said, like even if you do not state the positive sign, but just say the number, that is fine with science and math in general. The third way of expressing enthalpy is enthalpy as part of reaction. And then what do we have here, or as a term of the reaction, what do we have here is that in an exothermic, again, we don't use the negative sign in any of them, but we express it as reactants and products plus enthalpy change. And then for endothermic, we have reactants plus the enthalpy change, and then products. Okay, and the last part of it is using a diagram. I will just say potential diagram. And in an exothermic reaction, what do you have is that the energy is released to the environment. So in exothermic, you will have reactants, products, and in an endothermic, you will have reactants, products. So Z and S sign of it.